Okay, so here's the last video for um, class number 10. Right, so this is video 5, class 10, and we're going to talk about using siphons. Right, so we can use Bernoulli to find how much the siphon. So we're going to do problem, once again, out of Munson. This is problem 388. Water is siphoned from a large tank and discharges into the atmosphere through a 2-inch diameter tube, as shown in this figure. The end of the tube is 3 feet below the tank bottom, and the viscous effects are negligible. Right? So we can use Bernoulli because viscosity it can be ignored. Determine the volume flow rate from the tank, and then determine the maximum height over which the water can be siphoned without cavitation occurring. Atmospheric pressure is 14.7 psi, and the water vapor is 0.26 psi, right? So the water vapor pressure, right? So this is the pressure below which water will evaporate at regular temperature, right? At standard temperature. So you could look this up in the steam tables if you had a very complete steam table. This would be the pressure, the saturation pressure that you would get at let's say 60 degrees Fahrenheit probably. So I'm going to use Bernoulli 2 for this, and I'm going to go between here. We're going to call this 1. I'm going to call this 2. I'm going to reserve for that. And then right to here, I'm going to call that 3. And the reason why I could do this is because we can have a streamline that looks like that right there, right? So this is along a streamline thing that we're allowed to do. So let's do Bernoulli 2 because we haven't used it enough. Where we have P1 divided by gamma plus V1 squared over 2G plus Z1. And I'm going to do it between 1 and 3 initially because I need to find the volume flow rate. Well, I need to find the velocity. That's going to give me the volume flow rate. So we got P3 divided by gamma plus V3 squared over 2G plus Z3. So what's good now here is that this is going to be atmospheric and that's going to be atmospheric. So we can write that out. V1 is going to be the tank. We're going to pretend the tank is big enough. We don't know how wide it is, so it could be so large that this isn't going to be dropping or this is going to be so negligible so that we can go 0 right to there. And let's treat this as the datum. So we're going to say that is 0. And what we're going to end up finding is Z1 is going to be V3 squared over 2G. Notably, density or specific weight doesn't even come into play. And if you recall, this is really the Torricelli equation once again. 2G Z1. Right? Yeah. I have it written on my page the wrong way. I need to fix that. Z. No, I got it. I know I had it. No, I did have it wrong. There you go. I fixed it. I'm fixing it. Fixing it now. There you go. Hopefully I didn't do it in class. Probably did. All right, whatever, man. So what we have is 2 times 32.2. We are using US units, yes. And that Z, that's going to be 3 plus 9. I could do that in my head. That's 12, right? Yeah, sure. So V3 is going to be equal to 27.80 feet per second. But now we want to find the flow rate. Well, this is the 2-inch diameter. So we could find the volume flow rate by taking V3 times A3, or 27.80 times pi over 4 times the diameter, which is 2 inches, but we want to be in feet, so 2 twelves. And we end up with 0.6065 cubic feet per second. I don't know what that means. Let's turn it to a gallon per minute. So we get to 0.6065, and I'll say 7.48 gallons per cubic feet. Okay, so cubic feet cancels out. And then let's go 60 seconds per minute. So the seconds cancel out, so we get gallons per minute there. And we have now 272.2 gallons per minute. Wow, that's pretty impressive. That's just a 2-inch. Well, that's a 2-inch hose. That's it's a substantial hose. That's a pretty big hose right there. And then we want to do the second part of this. We want to worry about cavitation, right? So we could actually go between 1 and 2, or we could go between 2 and 3, right? Well, we want to find out here. But I think it's simpler to go between 1 and 2. Now, one thing you should remember is that this is going to have the same velocity as that. It has to, right? It doesn't have any choice. It's got the same flow rate. It's got the same cross-sectional area. So V2 must be equal to V3 because of the size of the hose of the thing. So between 2 and 3, we say that P, let's go Bernoulli 2 again. P2, this would be a 2, plus 1, not 1/2, sorry, it's going to be V2 squared over 2G plus Z2. Did I say 2 and 3? I meant 1 and 2. What? I guess I'm doing. Oh, no. Okay, I see. I know what I did. Okay, so this is actually easier this way. I got you. That's supposed to be a gamma. That's a gamma too, right? Plus V3 squared over 2G plus Z3. Now Z3 is the datum, right? So we can go that to 0. What's interesting here is that that guy and that guy got to cancel out because of this right here. Because these two are the same. Yeah. So that makes it like a little easier. This one's going to be atmosphere. So let's keep this in here right there. Right? As atmospheric pressure. Sure. Okay, so let's write this out. So Z2 is going to be 12 plus H, right? So it's because here's the datum 3, 9, and H. So Z. Let's see. No, P2. Let's see. I'm not arranging this the way that I want to. I don't like the way that I wrote it on my page, so I'm hemming and hawing. How do I want to write this? Well, down here I'll write Z2 is equal to 12 plus H. Okay, so there, I knew that right there. And here is just the approach I want to take to this right here. So we're going to say that P2 is going to be equal to the vapor pressure. Yeah, okay. So the vapor pressure is 0.26, and that's absolute, right? So we want to get down to 144. Yeah, I think I'll just write it out that way. I'll just write out the whole thing. I'll write it out the way I have it written above, and we can work it out, right? So we'll have 0.2, I just erased it, 144, and it's water, right? Water, yeah. So we go 62.4, all right? That's the way we have here. Plus, that's so we're gonna have 12 plus H is going to be equal to, now here we want to have atmospheric pressure, right? So that's 14.7, because this is gauge, this is absolute, and this has to be absolute too. And we have 144 and 62.4, right? And if we do that, what we end up finding, okay, so let's actually work through those numbers, because I didn't have the in-between numbers. I did it a different way. I kind of like this way better. So this is maybe straightforward. So 62.4, and we're gonna have divided, right? So this ends up being 0.6 right here, plus 12 plus H is going to be equal to, here's 14.7, 144 times, and then 62.4 divided. And so this is going to be 33.92 right there. So this is like the maximum that you can get from absolute zero, right? This is absolute zero. So we're going to come over here and we're just going to subtract that out, right? So that's not a lot compared to this, right? And then we're going to subtract out 12. And so what we're left with, oh, I don't think I did that right. So 33.92. Yeah, let me double check that. 0.26 and 144 times, and then 62.4 divided. Yeah, still get 0.6, and then 14.7, 144 times 62.4 divided. All right, still got the same thing. Subtract that, and now subtract 12. Yeah, okay, now I got it. All right, so I just hit the wrong button. 21.32 feet. So that's as high as we can get. That's a pretty high right there, right? Well, I guess with the velocity isn't that it isn't as high as you might think. Or I guess maybe really it's all about this guy right here. So this is very low pressure. So it's almost all driven by just what the essence of what water can do in terms of lift. This is also the distance that you could, the largest distance that you could possibly lift water, right? And you can't have a suction out of a pump and lift water any higher than that, right there, because that's really the feet in water column that are possible from, because you can't get the suction greater than absolute zero. So a lot of times we'll have like some kind of booster pump that's submerged booster pump when you have to like lift something that's larger than that, because it just simply can't be done. All right, so that was it for this. All right, cool. And hopefully this will help with siphon problems. And we did a lot of Bernoulli. And there was a lot of this Torricelli equation that resulted from here. But I urge you not to just jump to this equation. Work through Bernoulli so that you could see how it relates to your scenario, because it's not always clear. I think that's the best way to do it. So thank you.